We've been exploring a lot of different ideas around probability distributions and random variables and things like that. But of course, when we want to make algorithms concrete, we often need to be able to generate random variables from different kinds of distributions. So in this video, I'm going to talk about generating random numbers. Now, there are a lot of different reasons that you might want to be able to generate random numbers. So, for example, you might want to be able to perform Monte Carlo simulation. Monte Carlo simulation, as we'll see in a couple of videos, helps us estimate difficult expectations and perhaps solve challenging integrals. It's something that's used across many fields, not just computer science, but also various engineering disciplines, economics and physics and so on, to help us understand natural phenomena and to model different things that might happen. As you might have seen in other computer science classes, random numbers also help us generate randomized algorithms. That is, these are algorithms where by using randomness, they can get some interesting and nice properties and expectation. Some kinds of coding algorithms and sorting algorithms and things take advantage of randomness in order to go faster. Of course, randomness also comes up in cryptography, where we need to generate random numbers in order to contain secrets. And of course, there are lots of other uses as well. One notable one being something like games, where we might use random numbers in order to generate procedural terrain or implement the behavior of some non-player character. But where can we get random numbers on a computer? At a basic level, it seems really challenging because, of course, our computers are deterministic. And so there's no algorithms that we can come up with that are going to produce random numbers on the computer itself. Truly random numbers, that is. So instead, we often look outside the computer in order to try to generate randomness. That might come from mouse clicks or other kinds of properties of the user interface, or it might come from specialized hardware that you can buy that will generate random numbers using some physical noise on the device itself. It used to be that you could actually buy CD-ROMs full of random numbers that had been generated from some high-quality source. But of course, for things like Monte Carlo and randomized algorithms and games and things like that, we don't need true randomness that's really, really random. We just need sequences that have the nice statistical properties that we would expect a random sequence to have. And so random numbers that we generate deterministically on a computer, we call those pseudo-random numbers. And these again are generated from some deterministic algorithm on your computer that you initialize and then iterate, but that hopefully have nice properties. What I mean by good statistical properties is, if you were to take a sequence of pseudo-random numbers and you were to perform various kinds of statistical tests to compare them to a true random set of numbers drawn from some uniform distribution, then it would be difficult to disambiguate them. That is to say, they would tend to be distributed around the volume in the right kind of way, they would tend to be sort of uncorrelated with each other, and they wouldn't have repeating patterns that you might be able to detect. It turns out that generating pseudo-random numbers that have these kinds of nice properties is extremely difficult. And it should also be said that we have a different standard for what it means for something to be random when we're talking about various kinds of estimation tasks like Monte Carlo or generating something for games than we do for cryptography, in which we, in addition to having nice statistical properties, somehow need the sequence to be unpredictable in polynomial time. Now, there are good implementations of pseudo-random number generation out there for you when you want to do machine learning and statistics. In fact, things like NumPy Random are going to do the job for you most of the time. It implements a high-quality random number generator that would pass most of those kinds of tests we're talking about. I'm going to tell you a little bit about how one classic kind of algorithm in this space works, called a linear congruential generator, but I want to emphasize that you should never implement this kind of thing yourself. So there's different kinds of things in life that you should always take someone else's high quality implementation of, and random number generation is one of these. It is very hard to do this in a way that gets it right, and things that might kind of seem random can turn out to be flawed in complicated ways that are difficult to detect. So you should always use an off-the-shelf, high quality, well-tested implementation of random number generation. Algorithms for pseudo-random number generation usually have a particular kind of recipe. The recipe has a couple of different ingredients. It has some set on which you're trying to generate some uniform distribution. So let's call that output set, let's call that U. And then it also has some kind of finite state space. Let's call that S. Generally speaking, these are integers. So a typical kind of thing for U would be like the unsigned 32-bit or 64-bit integers. And the state space S might be similar or might be a little bit larger. And then the idea is to define a function, some interesting function f, say, that takes a point in S and maps it to another point in S. And then to define another function, let's call it g, that takes a point in S, so takes a state, and maps that to the output. So the idea being that f is going to evolve the state forward, and then G is going to take that state and produce an integer that hopefully is kind of statistically uniform. Then what we do is we come up with some initial S that we might call the seed. And the seed completely determines what this sequence is going to be. So once we apply F to the seed, then it gives us another state, and then we apply F to that again, and it gives us another state, and on and on and on. And then each one of those states, we can ask it to give us a piece of output. And the idea is that these states evolve in some interesting and chaotic way, such that when we look at the numbers associated with those states, then they'll be uniform on whatever set we decided to target. So we could think of this as being some state S0, and then we apply F, and we get, say, S1, and then this could give us a sample U1 if we wanted it. And then we could do this again, apply F to S1 to get S2, and then we could get another number U2. And we could iterate that off into the distance. Designing good Fs and good Gs is a hard thing, and this is the thing that I'm saying that you don't want to do on your own, but it's worth kind of understanding the way that these things work, broadly speaking. What's interesting from a scientific viewpoint is that the determinism actually makes it easier to debug random code than it might be otherwise. So a very, very common thing to do in any code that you run, and I think a lot of you are doing this already, is to set the seed of your random number generator at the kind of the very top of your script, so that then when you run it, you always get the same results, the same random results. Ideally, this wouldn't damage any of the statistical properties of whatever it is that you're doing, but it will make it a lot easier to debug because it'll be doing the same thing every time. So let's talk through a classic example of a pseudo-random number generator. This is not one you should use in practice, but it is fast and kind of represents the general space of these kinds of things. And it's called a linear congruential generator. So for an LCG, the state space would be some set of non-negative integers. So something like 0, 1, up to some m, that I'll get back to in a second, minus 1. So this is a set of m possible states. M is big, by the way, like say, 2 to the 32nd. And then we define the function f that evolves the state. We define that to be some a multiplied by the state plus some constant c mod, that is modulo, m. This mod m means that we're doing the arithmetic modulo m. That means that no matter what we do, we always land back in this state space. We call this the modulus. We call this the multiplier. And we call this the increment. And then the function g is just the state. So the random number that we get is just going to be that function s. So we initialize it with some s, and then we multiply it by a mod m, and then add c mod m, and that gives us a new state. Just to give you an idea of the kinds of things that people have proposed, then for example, one proposal for m is something like 2 to the 31 minus 1. This is for sort of 32-bit integers. And then a, maybe something like 2 to the 7th. And then one proposal will just have c being 0. So in this example, all you would be doing is taking your state and multiplying it by this number, and then taking the remainder after you divide by m. One thing that's important to think through is that necessarily these kinds of evolutions and pseudo-random number generators in general have some period. That is, eventually they loop back on their initial state. And of course, once it goes back to its initial state, then it produces the exact same sequence again. So pseudo-random number generators are periodic. It is important to the quality of a pseudo-random number generator what that period is. That is, how many pseudo-random numbers do you generate before you go back to the initial state again? Because of course, a periodic sequence doesn't seem very random. And so we'd like to only consume random numbers kind of before we reach that period. This one is an example of something with a period of something like 2 to the 31 minus 2. So this is appealing because it's fast and because it's easy to implement, but it actually doesn't have very good statistical properties. So when you use a modern pseudo-random number generator, behind the scenes, it's going to be doing a much more sophisticated kind of update, and it's going to have a larger state space so that its period is very long. A common kind of thing that you encounter in practice is something called a Mersenne twister, which is built around a Mersenne prime. Let's assume now that you've plugged yourself into a pseudo-random number generator that has a nice large period and a very large state space up to some number m. So essentially what you're doing is assuming that you have something that's giving you uniform numbers in, let's say, some large set 0, 1, up to m minus 1, where m is a really big number, like 2 to the 32nd. So the question is, how do I go from a uniform distribution on this huge set into an interesting, possibly non-uniform distribution on some other set? Let's start out with some baby steps. Let's imagine you wanted to turn that into a uniform distribution on a discrete set with only k outcomes. Now, of course, the very simplest thing you could do is you could take your sample u and find its modulo k. Now that's using the low order bits of u, and that has some subtlety that you might want to pay attention to in practice, but this is a good starting point for thinking about how you take from a uniform distribution on a large set to a uniform distribution on a smaller set. But you might have noticed that when you use random number generation in something like NumPy, that you don't get discrete outcomes usually. Your sort of basic workhorse is the function rand, which is giving you a number between 0 and 1. So let's talk about a uniform distribution. I'm going to say there's a half open interval between 0 and 1, and we would get that by saying that we take u and we divide it by m to give us a floating point number. And so we never get m, so this doesn't produce 1, hence the open interval, but u might be 0, and so that gives us a 0. And this is essentially how the NumPy rand generator is giving you random values. It's doing something like the Merson twister behind the scenes, and then dividing that by 1 plus the maximum number that that generator can produce. This really is the workhorse that we use for lots of different things. So this is the kind of rand function from NumPy random. This is usually the way that we think about random numbers in most of these other situations in statistics and machine learning. So I'm actually not going to talk about the core algorithm anymore where we're producing integers. Instead, we're going to assume that what we have is something that's giving us pseudo-random numbers that are floating points between 0 and 1. The question is, how do we take those and turn those into other kinds of interesting probability distributions that we might want to manipulate? So how do we go from this uniform distribution on 0, 1 into interesting stuff? There's a set of concepts that we'll sort of come to over and over again, which is kind of adding things up and looking at thresholds. So let's start off with a non-uniform distribution with k outcomes. So let's imagine that we have some little distribution over, let's say, A, B, C, and D, and they have some probabilities like this. Let's call this PA, PB, PC, and PD. And of course, those numbers all add up to 1. So if I want to take a number between 0 and 1 and turn it into one of those outcomes, but have it give us the right distribution, then what we're going to need to do is create another little kind of data structure. In particular, what we're going to do is build a sequence of thresholds. So let's imagine that we have the interval between 0 and 1. And what we're going to do is we're going to start at 0, and we're going to first put a line at the value PA. Okay, so this is a little bucket where if the number that we draw falls into that, then we're going to return the value PA. Now what we need to do is divide up the remaining amount among the rest of the possible outcomes. So I'm going to next put a line for PB, but it needs to be, instead of just PB by itself, it needs to be PA plus PB. So now if I fall into this bucket, I'm going to return B for my random number. Finally, I add one more value, which is now going to be PA plus PB plus PC. And if I fall into this bucket, then I'm going to return C. And if I fall into this bucket, I'm going to return D. So now all I need to do is build this sequence of thresholds. And when I draw from 0, 1, it always falls into one of these buckets. The idea, of course, being that the size of the buckets are proportional to the probability of that outcome. You can see how this would generalize to many different kinds of outcomes, and also how this maps onto the thing you've already done in the homework, in which you only had 2 possible outcomes. You had a threshold that was positioned somewhere between 0 and 1, and you looked to see which side of the line it fell on. That's just a concept that we can generalize to more than 2 outcomes. Things are much more interesting when we start talking about continuous random variables, though. And here we're just going to focus on one-dimensional continuous random variables. So what we need to be able to do is map from that uniform distribution into something else that's possibly not uniform. Our starting point is to imagine that we have some random variable with some probability density function. So let's imagine that this is p of x, some density associated with a random variable x. And what we want to be able to do is to take our numbers in 0, 1 and turn them into something that has this non-uniform distribution, but that is continuous. One of the most important concepts to realize is that even though this object has a non-uniform distribution, what we're trying to do is to sample uniformly from the volume, or in this case, the area beneath the curve. So recall that a property that we require of a probability density function is that it integrate to 1. So it's like every little speck of area here has to sum up to 1. And so what we could imagine then is that we're trying to draw uniformly from all of those little specks of area. And under areas where the density is large, then there will tend to be more of them. So if I sample uniformly from the area, then I will tend to prefer areas with more density. Now, there are a couple ways to operationalize this observation. The first one is to think about the cumulative distribution function. So if we integrate this function left to right, then we get another function that we often think about, which is the cumulative distribution. So this is a function that is monotonically non-decreasing, starts at 0, and always ends at 1. And so as we move left to right, this is telling us how much area we've encountered as we're going. So we start with 0 area. As we move right, we accumulate more and more until we have all of the area and we have 1. So one of the key ways we can think then about how to generate a uniform random variate under this area is to draw uniformly here between 0 and 1 using our rand function. So draw some point, and then look and see where that meets the cumulative distribution function. And that gives us some value. And that value is a draw from that distribution. So saying that again, this y-axis is representing the area underneath this curve. I want to sample uniformly from it, and I can do that with this function between 0 and 1, and I'm just asking the question, where does it intersect that CDF? Putting that in a little bit more notation, this is saying that we start with a PDF. Let's imagine that this is f of x, and this gives us a CDF, and I'm going to use a capital F to describe the CDF. And now what I'm doing is I'm looking at the inverse function of the CDF, sometimes called the quantile function. So this is the function that is going from sort of y back to the x-axis. And because this function is monotonically non-decreasing, then it gives us an answer. So now we have this function f negative 1 of some uniform random variate u. So this gives us a kind of algorithm in situations where we can find this function for some density we want to draw from. So if there's some distribution you care about and you want to sample from it, and you can find the inverse of its CDF, then you can apply that function to your output from rand, and that will give you a draw from that distribution. This is sometimes called inverse transform sampling. Let's walk through an example of inverse transform sampling, and let's do it with the exponential distribution. So just to remind you, the exponential distribution tends to look like this. The form of its density function is lambda e to the negative lambda x. Now if we want to come up with a way to take our pseudo-random variates in 0, 1, and we want to turn those into samples from the exponential distribution, how do we do that? Well, first, we compute the CDF. Now remember that the CDF is the integral from, in this case, 0 up to x of the PDF. And I'll say z here as my dummy variable. This is not too hard to figure out, and you see that it is 1 minus e to the negative lambda x. And if we were to plot this, it would look kind of like this, going up to 1 from 0. And of course, the specific rate at which it does that depends on lambda. Now let's think about how we would invert that. Let's imagine that we had some variate u, and we set that equal to the CDF. Then, of course, we wind up with something that looks like e to the negative lambda x equals 1 minus u as a starting point. And now we take the log of both sides, and we get a negative lambda x equals log, this is natural log, of course, 1 minus u, and then we can divide by negative lambda. So what does this mean? It means that I can draw from the uniform distribution between 0 and 1 and plug that in here for u, and then when I apply this function, I'll get an exponential random variate drawn according to lambda just by applying this function. Now you can probably see that there's some symmetry we can take advantage of. In particular, if I have a uniform pseudo-random variate between 0 and 1, and I say 1 minus that pseudo-random variate, then I get another variate that's uniform between 0 and 1. So I can instead, if I want to, I could write this as something a little bit simpler. I could just say that I'm going to take the natural log of u drawn from rand and divide that by lambda. So this is what that inverse transform sampling would look like. It's solving that intersection problem in a closed form way. This is a particularly nice example. Most of the time, the inverse of the CDF is not available to you. So if you have some sort of nice and well-behaved functions, then this is great and it's a nice way to do things, but it's not often the case that you're actually able to do things in this kind of nice closed form way. So I'll give you an example of another way to solve it. Let's imagine that you're in a situation where you're not able to perform inverse transform sampling. You have some PDF, maybe it has some normalization constant you don't know, but you don't have any kind of easy closed form access to its CDF or the inverse CDF. Then you might use a technique called rejection sampling. The idea of rejection sampling is to use our randomness on simple and easy distributions and then make decisions about whether or not to keep or reject the thing we generated. And it turns out then that when we keep a set of things, it will be from the right distribution. So let's imagine that we have some annoying density that we'd like to be able to sample from. And we don't have access to its inverse CDF. But what we do have access to is some other distribution and a constant such that we can put an upper bound on it. So let's imagine that we can put a Gaussian upper bound on this. So just to be totally concrete, we're going to say that this thing is f of x. And we're going to say that this thing is some distribution g of x, and then also there's a constant to make sure that it's an upper bound. And we'll call that constant c. Okay, so the situation, annoying PDF, upper bound from a simple thing that we can draw samples from, and we scale it so that it certainly is an upper bound. Remember from just a few minutes ago, we talked about how if we could sample uniformly from the area beneath the PDF, that would give us samples of the right density. In general, that might be hard, but what we could do instead is sample uniformly from this area beneath the upper bounding function, and then only keep the ones that fall inside this PDF. And because they're uniform on this superset, then they'll be uniform on the subset. So let's take a look at how that would work. What we would do is step one, we would draw from the G distribution. So that gives us some location. We get some sample. And now what we do is to get a uniform variate under the orange curve, we're going to imagine that there's some stripe going straight up like this, up to c g of x at that location. And we're going to draw uniformly on that interval, which is a thing we can do easily because we have access to simple uniform random variates. So I'm going to draw on this vertical line. If I draw beneath this purple fx curve, then I'll keep the sample. And if I draw above, then I didn't land in this area and I'm going to reject that sample. So if I throw down a point here, reject that. So I don't keep that one. Maybe I then next draw over here, and maybe I hit that and I keep that sample. And so then now I'm calling that a sample from this distribution. And I can iterate this over and over again where I draw from orange curve, draw beneath the orange curve uniformly, and then accept or reject based on that threshold. And if you keep doing this, the ones that you accept will be drawn from the uniform distribution that we need for this more difficult PDF. The downside of this method is that it can be difficult to find an upper bound, and it can be the case that if your upper bound is very loose, then most of the points that you draw will not be beneath this curve, and so it might take you a very long time to get points that you accept. In fact, it turns out that in high dimensions, this almost never accepts, and it's very inefficient, even if the bound is just a little bit loose because of the curse of dimensionality. But it's a nice thing to be able to do in low dimensional problems, and it's an easy thing to see how it might work in just one dimension. This is an example of a little bit more sophisticated use of our random numbers. In the first couple of examples we looked at, we just took our draw from rand and we turned that 1-to-1 into a draw from the target distribution. Here things are a little bit more complicated because we're actually hitting rand multiple times just to generate one value. So we draw perhaps once from g of x, and then we draw that vertical line, that's another draw from rand, and then we might reject it and go back into this loop again and draw 2 more and 2 more and 2 more until we eventually accept. So there might be a very large number of calls to rand just to get one successful sample. And this turns out to be something that comes up quite a lot, where a lot of the sort of cleverness of drawing from more complicated distributions arises from taking multiple steps. In fact, there's very large classes of algorithms that generate samples asymptotically by drawing from Markov chains. So they have a procedure that's not totally unlike this, but that actually is taking a random walk around the space in such a way that it converges to the right distribution. Markov chain Monte Carlo methods, or MCMC, are sort of out of scope for this class, but they're extraordinarily powerful and important algorithms for sampling from high dimensional and complicated probability distributions.